In this video, we're just going to prove these given identities, and so let's get right to it. We have tangent squared of alpha times the quantity 1 plus cotangent squared of alpha is equal to 1 over 1 minus sine squared alpha. And we need to prove this or disprove it. The reality is most of these will just be prove that one side equals the other. And so I need to pick which side to simplify. I'm going to pick the right-hand side to simplify. So I need to show that I can modify this fraction to look like the stuff on the left-hand side, which means I'm working on the right-hand side only. And so we will not touch the stuff on the left. I don't know that this is the fastest way to do this. You could just as easily simplify the left side and show that it will equal the right side. And this process right here is up to you. So I know that 1 over 1 minus sine squared looks a heck of a lot like a Pythagorean identity. I know that sine squared alpha plus cosine squared alpha equals 1. So if I wanted to make this look like 1 minus sine squared alpha, I would have to subtract sine squared alpha from both sides, and I would get cosine squared alpha is equal to 1 minus sine squared alpha. So it's totally fine for you to go through and make these little notes along the way to make sure that you're making good choices for your substitutions. This gives me 1 over cosine squared alpha. Now I need to figure out how I can break this apart. I need something that's equivalent to cotangent squared alpha. I know that a sine squared alpha plus cosine squared alpha is equal to 1. That's tricky. And so I'm going to use that as my numerator over cosine squared alpha. Now I need to figure out what to do next. If I were to factor out a sine squared alpha out of the numerator, would I get what I wanted? I want to take sine squared alpha out of the numerator. I would have 1 plus cosine squared alpha over sine squared alpha left. I hope that makes sense. If it doesn't, ask yourself this question. If I were to distribute the sine squared alpha back in again, would I come up with what I had right here before? And the answer is yes, I would. Now I'm going to take that sine squared alpha times the quantity 1 plus cosine squared alpha over sine squared alpha, and I'm going to rewrite it as sine squared alpha times 1. Now remember, cosine squared alpha over sine squared alpha is equivalent to cotangent squared alpha. Oh, this is looking so much better. All over cosine squared alpha. Now, what's sine squared alpha over cosine squared alpha again? That's right, it's tangent squared alpha, and so I have tangent squared alpha times, now remember, I took this right here and I turned it into tangent squared alpha, the sine squared alpha over cosine squared alpha, and then the rest is 1 plus cotangent squared alpha. And hey, look at that, they match. All right, I might be getting a little excited about this, but this is so much fun once you see the pattern. It's so annoying until you can start seeing these patterns. And trust me, this could take like 3 or 4 attempts of trying things and they not working. And so then you have to erase it and start over. It's a good idea to have an eraser next to you so you can work through these. So I'll put the little box there and move on to the next one. The next identity we need to prove is tan t minus cotangent of t all over sine t cosine t is equal to secant squared t minus cosecant squared t. Clearly the variable is t, and we need to show that we can morph or modify one side to look like the other. I don't know that one side is easier than the other, but I'm going to go with the fraction this time. I'm going to try and morph this fraction on the left to look like the right-hand side. So I'm going to be working on left-hand side only. If this looks overwhelming, it's always a good practice to rewrite these. What I mean by that is if you have tangent of t, that's equal to sine of t over cosine of t. And cotangent of t is cosine of t over sine of t. And then in the denominator, we have sine of t, cosine of t. Notice I haven't modified the left or the right-hand side at all. I've just rewritten the left-hand side to look like stuff we're a little more comfortable with. If we think of this as this denominator's denominator, sine of t, cosine of t, over 1, we could multiply the denominator's fraction by the numerator fraction by flipping the denominator over and multiplying. If I were to distribute this fraction through, I would have sine t over sine t cosine squared t minus cosine of t over sine squared t cosine t. I'm going to reduce out the common factors. So my sine of t's divide out, my cosine of t's divide out in the second fraction, and I'm left with no more room here. So I'm going to keep working on this. Remember, I'm trying to show that it's equal to the right-hand side, and so my equal signs are still going to be on the right side of my work. So now I will have 1 over cosine squared t minus 1 over sine squared t. Now remember, I'm trying my darndest to get it to look like the right-hand side. So far, I've turned my common trig functions into things that are very similar to secant squared of t and cosecant squared of t. The only problem is I need to morph them. So 1 over cosine squared t is secant squared t minus 1 over sine squared t is cosecant squared t. And this is equal to the same thing on the right-hand side, secant squared t minus cosecant squared t. And we have proven the identity as desired, so we put the little square there. The next example we have is secant of x plus tangent of x over secant of x minus tangent of x is equal to 1 plus 2 sine of x plus sine squared of x all over cosine squared of x. Oh my goodness. If you feel overwhelmed, it's completely normal to feel this way and to feel like you don't know where to start. The best thing to do is just pick something If you see a pattern, go with it. And if you don't see a pattern, try looking at your Pythagorean identities or try rewriting one side so that it's all with respect to sine and cosine. If I look at my fraction on the left, it is not in terms of sine and cosine, but on the right it is. So let's pick the left-hand side to try and simplify and see where it goes. That means I will be working on the left-hand side only, which means I'm going to not touch the right-hand side. First, I'm going to rewrite this fraction as, on the left, as ratios or reciprocals. So secant of x is equal to 1 over cosine of x plus sine of x over cosine of x. And in the denominator, I have secant of x, which gives me 1 over cosine x, minus sine of x over cosine of x. I think it's extremely convenient that our denominators in both the numerator and the denominator match. And I'm going to rewrite these as fractions for the numerator and the denominator. I have 1 plus sine of x over cosine of x, all divided by 1 minus sine x over cosine x. That means I can divide out those common denominators. Ta-da! Just like that. And I get 1 plus sine x over 1 minus sine x. And again, make sure you put that equals sign there to show that you're trying to make it look like the right-hand side. Now, if I were to compare this to the right-hand side, I'll just go ahead and write it up here again. 1 plus 2 sine x plus sine squared x all over cosine squared x. I can see that this has a quadratic form to it. And so my guess is that if I multiply the left-hand side by a conjugate, I'm going to get something similar. But if it was a conjugate, would that work? I need something that's equivalent to cosine squared x in the denominator. So if I were to multiply the denominator by a conjugate, I would get 1 minus sine squared x. And that is exactly what I need. Because now my numerator will be quadratic in form and my denominator is going to be equivalent to cosine squared x. This takes so much practice, and I hope that you can see that it would be beneficial to work these out again on your own and see if you can make the left-hand side look like the right-hand side every single time. So when I multiply that 1 plus sine x in the numerator and denominator, I'm going to get 1 plus 2 sine x plus sine squared x all over 1 minus sine squared x. And that is so close to the right-hand side. The next step is just to modify this 1 minus sine squared x into a cosine squared x, and I will have what was requested. In this case, we have cosine of x over 1 minus sine of x is equal to 1 plus sine of x over cosine of x. In this case, it doesn't matter which side you pick because they're almost reciprocals of each other. Almost. The exception is this plus sign here. So I'm just going to pick the right-hand side to show that I can make it look like the left-hand side, but you could certainly do something else. So I'll be working with the right hand side, which means I'm not going to touch the left hand side. I'm just going to modify the right side. I'm going to multiply by maybe a conjugate in the numerator. I'm not sure if this will work, but I'm going to give it a try. 1 minus sine of x over 1 minus sine of x. If I multiply the numerators together, I'm going to get 1 minus sine squared x. And in the denominator, I'm going to get cosine of x times 1 minus sine of x. Notice that 1 minus sine squared x is very similar to a Pythagorean identity. Sine squared x plus cosine squared x equals 1, which means if I wanted to find cosine squared x, it would be 1 minus sine squared x. So the numerator is equivalent to cosine squared x, and I'll just rewrite the denominator. Cosine x times 1 minus sine x. Now I can see that the numerator and the denominator have a cosine in common. So I'll have cosine of x over 1 minus sine x. And hey, look at that! It's exactly the same as the left side. And so we have proven that the identity holds as desired.